Hello. Okay. Sorry. Ditching out on you again today. The sun is not feeling well. I'm going to talk to you about equipotentials, which are almost exactly like what they sound like. We learned about potential as the potential energy per unit charge. And we're going to talk about, and basically we're going to look for places where they're equal. So it's just points where the potential value is equal. It's like it sounds. So if I have like a point charge here, and I choose like a point over here, I can solve for what the potential is using K, Q over R. Now, let's say I got some value. Well, if I was anywhere that was the same distance away, I would get the same value. So all those points would all have the same potential value. This line is an equipotential line. Sometimes they call them surfaces because really, if they're in 3D, they'll have like more of a contour than a line. But that's okay. So all of the points in the dotted line that I drew all have the same value for potential. So that also implies something about the work done between them. That means that the work to move along on an equipotential line or surface is 0. It's not going to do anything. I guess it's not really the empty set, but still, it's 0. So if I can move anywhere along here that I feel like, as long as I don't move any closer or any further, and I won't have to do any particular work. Same with a charge. If I put a charge, I can move it anywhere along the equipotential line without requiring additional work. That sort of makes sense. If I move it away, a test charge, I won't have to do any work. It'll actually, the field from the charge will do the work for me. If I move closer, I'll have to do work to get my test charge there. And the work that I do is equal to QV. Well, delta V, I should say. Okay. If I have no change in potential, then I don't have to do any work. Let's redraw this example right here with a bunch of equipotential lines. So we'll have one here, one here, and one here. And I'm going to assign them values. Usually you can actually figure out what they are by giving the charge and the distance. So that'd be 1, we'll say this is 1 volt. This is, or we'll say, no, we're still going to say this is 10 volts, 5 volts, 0 volts. I could have a -5 or a -10. I just chose those values. So a test charge that's brought here, if I put a test charge here, it'll move this way. Okay. And the work that the field does to get from this point to this point over here is the amount of charge that it has, Q times 10 volts. If this test charge was a proton, the work would be the charge of a proton, 1.6 times 10 to the -19th, times 10 volts. So it can seem as obvious as you think. 1.6 times 10 to the -18th joules. Remember, a volt is a joule per coulomb, so it's telling us how much potential energy per charge. So that would be the amount of work done by the field. If I took a proton and moved it from there to there, I would have had it. And I guess technically, I'm going to go back to this example real quick. Technically, I moved negative 10, negative, which implies that I didn't have to add any work done, that the field did it. The field did it. Now, if I move this over here, if I move from the 5 volt equipotential surface to the, to the 10 volt, in that case, with a proton, I'll have done 1.6 times 10 to the negative 19th coulombs. That's the charge. But I'll have moved up, so it'll be 5. That's going to be 8 times 10 to the negative 19th joules. You can see we gain energy doing that. Now, if we were to draw the... So next, let's talk about the relationship between equipotential and electric field. Well, we know that the relationship between field and potential, for, let's say, for a point charge, the potential is going to be kq over r, and that the field is going to be kq over r squared. Of course, this is a vector, so it's going to go in the r direction. This is not a vector. It does not have a direction. So, equipotential. And if you looked at the field for that positive charge, we would get a field that went like, oh, come on. We get nothing here. Nope. All right. Oh, there we go. Okay. So we'll get field lines like that. But if we look back at our equipotential, they were like this. So since the field moves in the direction of decreasing potential, in this case, well, in all cases, then the electric field magnitude or direction is always perpendicular to the equipotential line. Make a curve right X, I add 10. Trouble themselves. But if I stop and over there, that was the electrical and what the electric field. What volts will say this will make